Hi, welcome to the notes for H6-1, solving systems of equations with three variables. So in this lesson, we started out with a warm-up, and we were just asked to solve the following system of equations using any method. And when you look at those equations here, you have 12x minus 2y equals 16, and 30x plus 2y equals 68. So it's looks like two lines there. And when we talk about any method here, remember, you know three methods for solving systems of equations there. You know the graphing method. You know the substitution or equal values method. And the third method you know is elimination, also known as the addition and subtraction method. And elimination is the one that we're going to focus on here right now. Right? Since we have 12x minus 2y equals 16 and 30x plus 2y equals 68, if I want to do elimination, this is already set up for it here. Remember, we have opposite values. We have the negative 2y and the positive 2y. So if we add these two equations together, the y's eliminate, leaving us with 42x's. And then we have 84 on the other side. So 42x equals 84. And when you divide both sides by 42, you should end up with x equals 2. Now remember, you have two variables, so we're not finished. We need to take it here, and we need to use the information that x equals 2 to help us find our y value. So we're going to do 12 times 2 minus 2y should equal 16. So as we look to solve that there, right, we should have negative 2y should equal negative 8. And then when you divide each side by negative 2, y equals 4. So you have an x value, you have a y value there, and when we write our answer, we write it as an ordered pair, 2, 4. And that is the intersection point between the two lines, or those two functions there. Okay, this is something you probably did a lot of in either pre-algebra, algebra 1, maybe some in geometry here. Okay, so we're revisiting it here in algebra 2 as we build into a more challenging concept here. So just a brief bit more of review. So since we've been solving systems of linear equations in the past, remember that just means that we're looking at the ways that two lines can intersect in a coordinate plane. So one of those ways here, right, they can intersect at one point, and that's kind of like the situation we just did in the warm-up. We get that ordered pair as our answer. That's because we had, when you have two lines, they can only intersect in one point like that. Now the two lines there, we have them, they can go and not cross at all. So they can have 0 intersection points, which then would give us a solution that is no solutions. And if you think about that scenario, right, that's going to be when we have parallel lines. Two lines with the same slope but different y-intercepts. And then the third situation here, we could end up with an infinite number of points there that they intersect or they share. And, we call that infinite solutions. And that also happens here, in a coordinate plane when we have what we call coinciding lines. Coinciding lines, like parallel lines, have the same slope, but coinciding lines also have the same y-intercept. So it's almost like you have two lines that are directly right on top of each other. So they share all of their points. And that's when we get infinite solutions. Hopefully that is a good refresher here. Let's talk about solutions in different dimensions. So we're talking about a one-dimensional equation. Okay, that's something like, let's say 6x is equal to 18. If you're trying to solve that, right, we're trying to get x by itself. We get x is equal to 3. So we had one variable in our equation here. We get x equals 3. And if we wanted to represent that graphically, right, we just need just one axis here. So we'll put our number line down like it's our x-axis. And our solution would be 3, so we put a closed circle at 3. Now, you've done a lot with 2 dimensions in the past as well, just like the ones we just did, right? So we're going to add on to that x-axis. We're going to put the y-axis on there too. And remember, when you have solutions like this is what we call an ordered pair. Okay, so it is in a specific order, those pairs of numbers there, because our x-coordinate, let's say the x-coordinate was 3, and the y-coordinate was 2, right? That's a specific location on our coordinate plane where that point's located. So we have the point 3, 2. Now, if we climb the ladder into something that may be a little bit more new to you here, we're going to be looking at 3 dimensions. Okay, and so what we call a solution where we have 3 dimensions, x, comma, y, comma, z, we're going to call that an ordered triple. Okay, we're going to call that an ordered triple because it's got 3 dimensions. And 3 dimensions, if you think about it there, I know a lot of students have probably seen 3-dimensional movies, right? That's where you go to the movie theater there, and usually you watch the big screen, but when you put on the goofy glasses there, the images come off the screen towards you. Okay, so that's 3 dimensions. We're going to add some depth to it. So we're going to add our z dimension here. So you see here we still have our x-axis here. We've kind of angled it to the side. Same thing with our y, and that's because when we're drawing 3 dimensions on a 2-dimensional sheet of paper, it becomes a little bit more challenging. So we've got our 2 dimensions there, and then our z dimension here, right, it kind of comes up off of the paper, goes down below it there. If we had the ordered triple, let's say we'll use 3, 2, 4, right? That 3, 2, because we just graphed 3, 2 on the previous graph, would probably be somewhere like right here, right? So if you're kind of comparing these 2 graphs. But then we have to take into account, the z-axis there, where it's going to come up off of the paper here. So it would climb up 4 units. So if we went up 4 units here, it would be, it's going to come up here, and it's going to be like it's off of the paper in the air. It's like it's floating. Okay, now there are certain kinds of graph paper for doing 3-dimensional graphs and things here. This is really not one of them that's really easy to see that I have, but maybe we'll get some of those out for you sometime this week so you can see those. All right, so when we're dealing with things, when we come out of the traditional coordinate plane, right, and we go into space, right, when we're talking about space, we're talking about, an infinite number of sets of planes that are intersecting. So our lessons today, that when we're solving our systems, we're going to be looking for the intersection points between planes. And what I have for you here is just a diagram here where it's illustrating different ways that 3 planes can intersect. So this first example on the top left, you see I have planes A, B, and C, and they intersect at exactly 1 point. So 3 planes can always intersect at exactly 1 point, and that's an ordered triple, x, comma, y, comma, z. But there are other cases here. Here's an instance here where our 3 planes will intersect to form a line, right? So they can intersect in a line. And normally, when you have a line, you have an infinite number of points. And that's still the case here. So this is going to be an infinite number of points along a specific line. And because we don't really have, any coordinates or anything on these illustrations here, we don't have to give the specific equation for the line. But, sometimes you're working through it, you will need to do that. So we have an infinite number of points along a specific line. Now below, you're going to see here we have our, same planes. We have planes A, B, and C again. And what you come across and see here is that planes A and B intersect right here, forming this line. And planes A and C intersect to form that line. But nowhere on this graph do you see any points that fall into all 3 of the planes. Therefore, this would be an example of no solutions. Excuse me. All right, so this last example here is just another illustration of where you've got some different intersections between different planes. However, there aren't any points on here that are contained within all three planes, so this is just another example of where you will see no solutions. And we'll look at these types a little bit more tomorrow in the next lesson here. Okay, so today we're going to focus a little bit more on this first example up here. So let's jump right on into one of our problems. I'm only going to do two here because I don't want this video to be too long, and I've already recorded it twice. Once without sound, and the other time I forgot to press record. So hopefully third time's a charm, right? All right, so direction state. Solve the following system of three equations. So you notice here we have three variables, right? Therefore, we need three equations. That's very important to remember. Okay, anytime you're dealing with three variables, you need three equations. Now, these ones are all kind of written here. All the like terms are lined up. If you're somebody who's usually not very neat in doing your math work, you need to work on that here. This is going to be an important concept here that you really need to push yourself to try to be neat and organized. To help us, what I'm going to do here is I'm going to label each of my equations so you know which one I'm talking about. So I have A, B, and C. You should label those on your paper as well. So for those of you who like steps, following steps and things here, I'm going to write out kind of like some procedures for you. The first thing that we're going to do here is we're going to choose a pair of these equations and eliminate a variable. So choose a pair of equations and eliminate a variable. So when I look at these here, I'm going to look here, let's say A and B to start out, because I've got this 3y and this negative 3y. So it's not going to require much work for me to set up elimination and do it there. So let's do that here. I'm going to recopy my two equations, A and B. I've got 2x plus 3y plus 3z is equal to 6. I've got a 6x minus 3y plus 4z is equal to 12. So for elimination, I'm going to go ahead and put my equal bar there to show that I'm adding the two equations together. Remember, the 3y and the negative 3y are going to eliminate. So what we're going to be left with here is 8x plus 7z is equal to 18. Now that's an important equation here, so I'm going to go ahead and box that in. And I'm even going to label it too. I'm going to give it its own letter. I'm going to call it equation D. Now, the second step here that you're going to want to focus on, okay, now after you've done that, you've chosen two equations there and you've eliminated one of the variables, now you need to choose a different pair and you need to eliminate the same variable. So we're going to choose a different pair and eliminate the same variable. That's extremely important there. Okay, the same part there. If you don't eliminate the same variable, then you're going to be just pretty much dead in the water. You're not going to be able to do anything after the next step. So because I also have, a positive 3y and another negative 3y, I'm going to go ahead and choose equations A and C, okay, and eliminate the y's there as well. So to do that here, I'm going to just recopy A one more time. 2x plus 3y plus 3z is equal to 6. And then we've got equation C, which was 2x minus 3y plus 2z is equal to 6 also. Go ahead there and eliminate your y values, and you're left with your 4x plus 5z is going to equal 12. And we're going to box that one because it's important as well. All right, now when you focus here on the fact that you've got equation D and equation E, two equations that each contain the same two variables. So we just have a system of equations now that we can solve to find our x and our z. So our third step for you procedure people here is we are going to solve for x and z by solving the system that contains D and E. Okay, so we're going to focus on those here. So if I want to solve these here using elimination here, right, I got a 4x and an 8x. So I could multiply my equation E by a -2 and then do elimination. So that's what I'm going to do. I'm going to recopy my D here. I've got 8x plus 7z is equal to 18. And I'm going to take -2 and multiply it times E. And you notice what I'm doing here is I'm illustrating what I did. I'm doing -2 times E. So -2 times 4x is -8x. -2 times 5z is -10z. And then -2 times 12 is -24. By putting this little label here, this helps me to remember what I did. So if I made a mistake, I can go back and double check. If you're not going to take the time to label your equations there, it's going to take a lot longer to find your mistakes. So what I end up here is -3z is equal to -6, so our z is going to equal 2. Now we'll take that 2 here, and we're going to substitute it right back into D or E to figure out what x is. And it's your call which one you use. I'm going to use E here. So 4x plus 5 times 2 is equal to 12. So 4x is equal to, what, 2? So x is going to equal 1/2. All right, so now I know that z is 2, x is 1/2, and I can do my next step here. I'm going to solve for y by plugging in the values of x and z into one of the original equations. But what I mean by originals is A, B, or C. So let's say here, I'm going to just use A. That one looks fine to me. So I'm going to say my equation A here, I'm going to do 2 times 1/2 plus 3 times y plus 3 times 2 should equal 6. So we have 1 plus 3y plus 6 is 6. So we get 3y is equal to -1. So therefore, y is going to equal -1/3. So now we've got answers for x, y, and z, and we can take it here and we're going to plug them in into the ordered triple in that order. So 1/2, -1/3, comma 2. This is our solution here. Now to be able to check it, right, we used equation A to find our value of y, which means then you need to take it and you need to plug in all three of those into B and C to check them. So the last step, in that little process there is to check it by plugging it into the other two equations. Don't settle for just one, because many times when we make an error, the points will check out in one of the equations. Sometimes they'll check out in two of the equations and not the third, but they have to have all three of them in order for it to be correct. And it only takes a moment to plug them in and check it there. I'll do it on this one here just because I want to make sure that you understand what my expectation is. So I have 6 times 1/2. So this is equation B. I have 6 times 1/2 minus 3 times -1/3 plus 4 times 2 is equal to 12. That's going to give us 3 plus 1 plus 8 is 12. Therefore, 12 equals 12, and we know that that one is correct. And then let's do C here. So for C, you're going to do 2 times 1/2 minus 3 times -1/3 plus 2 times 2 should equal 6. So 1 plus 1 plus 4 equals 6, and that is a true statement as well. We know that this answer that we've come up with here is the correct answer. That's the great thing about these problems. You know if you got it right or wrong. All right, so I know these are long and tedious there, but you know, you'll get faster at them there, and you can find some shortcuts in your writing there as you get better at them. I'm going to skip over the second problem here. It's an easier one. You can do it and then ask me about it in class there if you'd like me to check your answer. You can check your own answer as well, which would probably be the better thing, but I'll help you find your mistake if you come up with one. We're going to do this last one here. This one, the numbers are just a little bit messier, and that'll be a good practice for us. If you want to take it and pause the video right now and try it on your own, that would be an awesome thing to do. Then you can go back and see if you made a mistake, or you're good to go if you checked it afterward. So let's go ahead here and do it. I'm going to go ahead and label my equations A, B, and C. You can label them 1, 2, and 3, whatever you want to do. If you have A's, B's, and C's in your equations, then you probably don't want to call them A, B, and C. You probably want to call them something else. A, B, and C should be fine here for this one. Now, when we look at this one here, we have to look at what variable we want to eliminate. So when we look at our x's here, right, 2 is not a factor of 5, 2 is not a factor of 3, 3 is not a factor of 5. So we're going to have to do a lot of manipulation to our equations in order to eliminate an x. So that might not be the best choice for us. When we look at our y values, I have a 2y. 2 is a factor of 4, so I can multiply that middle equation by a positive 2 to get positive 4y, and then I could eliminate. Or I could, go down here and multiply it by a 3, so I have 6y and negative 6y. So y is a good candidate there for elimination. And z will be also, right? Because I have just a single z here. So if I multiply it by 6, then I can eliminate it with this one. Or if I multiply it by positive 5, I can eliminate it with that one. So you can use either y's or z's for elimination here. That's up to you. I'm going to go ahead and use the y's right now. And I'm going to go ahead and eliminate that y from equations a and b here first. So a is 5x minus 4y minus 6z is equal to negative 19. For my b, remember here, in order to make this into a positive 4y, I need to multiply it by 2. So I'm going to list here that I'm doing 2 times equation b. So after I do that there, 2 times negative 2x would be negative 4x. 2 times positive 2y would be positive 4y. 2 times z is obviously 2z. And then 2 times 5 is going to be 10. Now let's do our elimination. The 4y and negative 4y are going to eliminate, leaving us with just an x. Minus 4z is going to equal negative 9. Let's box it because it's important. Call it equation D. And now, because I was using this 2y here before, I can multiply that times a 3 and eliminate it from, the equations between B and C. So let's go ahead and do that here. I'm going to go ahead and copy down equation C because it doesn't need to change. So 3x minus 6y minus 5z is equal to negative 16. And then when we do 3 times b here, we now have negative 6x plus 6y plus 3z is equal to 15. Do your elimination. So what I'm left with here is negative 3x minus 2z is going to equal negative 1. And we'll call that equation E. To solve for x and z here, okay, I could go ahead and do elimination between the two equations to get rid of the x's. So I'm going to multiply equation D by 3. So we have 3 times equation D. So we're going to have a 3x minus a 12z is going to equal negative 27. I'm going to bring my e equation down, so negative 3x minus 2z is going to equal negative 1. Go ahead here, eliminate. So remember, this time you're eliminating your x's. Therefore, we have negative 14z is going to equal negative 28. Divide each side by negative 14. So z is going to equal 2. Go ahead now, find your x values. I'm going to plug it into d. So I have x minus 4 times 2 equals negative 9. So we have x minus 8 equals negative 9, and x equals negative 1. And then we're going to take it here, and let's use whatever equation you want. I think I'm just going to use b here because the numbers look smaller. So negative 2 times negative 1 plus 2y plus our z, which our z is 2, should equal 5. So 2 plus 2y plus 2 is 5. So 2y is equal to 1, so y is going to equal 1/2. So for this one, it looks like our ordered triple is going to end up being negative 1, comma, 1/2, comma, positive 2. And for checking purposes here, right, so we used b to find our last value, so you'd want to check it with both a and c. I'm not going to check right now. I'm going to tell you those ones are correct because this video is long enough. But hopefully, if you have questions, you write them down. Please bring them to class. Thanks for watching. I hope this helped.